Hey scholars, it's good to be back with you. This is another in a series of videos about Mathcad Prime version 11, which is the newest version as I'm recording this. And today I'd like to go over symbolic processing. Now symbolic processing is just all kinds of handy. Once you start using it in Mathcad Prime 11, I think you're really going to like it. I use it a lot. My students use it a lot. If you're unfamiliar with symbolic processing, that's kind of what you're doing when you're writing stuff down on a piece of paper, when you're doing an algebra problem or a calculus problem. When you're pushing symbols around instead of numbers, that's symbolic processing. And there's a very good symbolic processor in Mathcad Prime. There's two ways to access it here. If you go to the Math tab right up here and click under Operators, see that right arrow right there that says Symbolic Evaluation? That's an equal sign, and that's where you're telling Mathcad, I want to know something, but I want to know it in symbolic terms, not numerical terms. Now you'll notice there's a whole Symbolics pull-down menu right there. There's that right-hand equal sign again, or right-hand arrow that makes the symbolic equal sign. And here's all these modifiers and keywords you can use. I'm not going to go through all of them, but I will go through some of them for you. Now the keyboard shortcut for the symbolic evaluation is Control Dot. Now why Control Dot? I don't know. There's a limited number of keys on the keyboard and somebody decided to do that. So it works as well as anything. In this video, I'll click on the arrow sometimes and I'll use Control Dot sometimes. Let's try something simple first. Let's try multiplication. So if I say x equals, where you tell me something, it's giving me an error. It said, well, you haven't defined x. I don't know what it is. Good point. Let's try this. Let's try x plus 1 and x minus 1. And I'm going to go up to Symbolics, and I'm going to click right there. It just gave me my input back. That's not so good. Could I get it to multiply this out? Sure. I'm going to say expand, or I could have picked the expand button right there if I wanted to. There it is. Well, let's see how far we can go with this. That's pretty good. Let's make that to the, I don't know, third power. All right, so this is getting kind of involved. Well, what if I had this? Could I factor it and get that? You bet. So let's go, I'm going to hit Control equal, or Control Dot here. There it is. And see there's this gray bar up here for me to type in a modifier, some keyword if I want. So let's type in factor. And there it is. Now, if there's more than one variable on the left side, you can say factor, comma, and then tell it which variable you're interested in. Because I've only got x here, it just defaults to x. All right, so that's pretty handy. Let's try something harder. Can we try a derivative? Let's do that. So I'm going to go up to Operators here and pick the derivative operator. In fact, I'm going to expand this out just a little more. Maybe that'll help. All right, so derivative with respect to x of, I don't know, let's pick something. Okay, there's that. Control Dot. Okay, there it is. Now that's not too hard. Anybody who's taking a calculus class could do that. Let's try something else here. There we go. Take that squared. All right. And let's maybe plus sine x. Okay, there it is. So far, still not very hard. I'm going to highlight that whole thing. And let's square that. There it is. Oh boy. Can I keep going with this? You bet I can. Okay, and this just keeps getting longer and longer and longer and longer out here. I can stretch it out and see where the end of this expression is. It just keeps going. Whoops. Let me back up here a little bit. Sorry, there it is. There's the whole thing. Okay, that's pretty noxious. Now, this is very involved, but there's a difference here. There's a difference between tedious and difficult. Is this tedious? Yes. Is it difficult? No. If you know some basic rules of calculus, of taking derivatives, so like a product rule and a chain rule, you can grind this out for yourself. It'll take a long time, but it's not very hard. So it's tedious but not difficult. This will save you a lot of tedium. All right, let's try something else here. Okay, sine x plus 1, and plus x. And maybe we'll square the whole thing. I'm having trouble here. There we go. Okay, there's the derivative. Now if I click here, notice there's a little box up there. What if I want the second derivative? Okay, third derivative. We can just keep going forever. I don't know how far this will go. I don't know why you'd ever need the 12th derivative of anything, but there it is. Now this does need to be an integer. There is such a thing as fractional order calculus. I don't think this is going to work. Nope, it croaked. Okay, well, unsurprising. Okay, so there's a second derivative for you. If it'll do a derivative, will it also do an integral? Well, sure. So let's click right there, and let's take something really simple. So there's a very simple parabola. Well, I got to give it a variable, so I'll give it x and hit Control dot. Well, there's the integral. Well, that's not too hard. We can figure that out on our own pretty easily. Well, let's make this a little harder. Let's put parenthesis around that and multiply that by sine x. Okay, that just got harder. Now, the integrals are a lot harder than derivatives because they're an inverse function. Derivatives, you go forward through the problem, and you just apply the quotient rule or the product rule or the chain rule to find the derivative of a function. When you're doing an integral, you're giving it a function and saying, find me another function whose derivative is this. In fact, your calculus teacher may even call this an antiderivative at some point in the class. So when you're starting to do integrals like this, there's all kinds of techniques and things you have to use to try to get from here to here. And they are tedious. Sometimes they get difficult. Well, by offloading this to the symbolic processor in Mathcad Prime, you save yourself all that work. So let's try one other thing here. Oops. There we go. Ooh. All right, now we're getting into, I'm not sure what that is, error function, I think. We're getting into some pretty rarefied territory here. So the fact that you can write down the problem doesn't mean there's a clean solution to it. So let's get rid of this again. And maybe let's leave it like that. Now when I click on the integral sign here, notice there's these two boxes here. I can apply upper and lower integration limits. Now I hadn't so far. This is an indefinite integral. I can make it a definite integral if I want to. So if I go from, now let's make it from A to B. That's what you see in your calculus books a lot of the time. Well, there it is. Kind of long, but there it is. There's more of it out there. Could I put a number in there? Sure. Let's put a 0. Okay, now it's back to something a little more compact. What if I say 0 to 1? There. Now notice it gives me cosine of 1 right there. That's 1 radian. And sine of 1 right there. It doesn't give me a number. It gives me that. Let's try something. Will it let me do this? Yeah, there it is. I typed in an equal sign, a regular numeric equal sign, and it told me a decimal number that's equivalent to that. Right? It actually evaluated it for me. That's pretty handy. So on this side of that equal sign, on this side it's symbolic. On that side it's numeric. And I can even go up here and I can ask for more decimal places if I want. Now this is very different than MATLAB. MATLAB has a pretty hard line between symbolic and numerical processing, and you've got to track both of them fairly carefully. You can go back and forth between the two, but it's not seamless. This is seamless. This is amazing. Let's try something else. Most of you know what a Taylor or MacLaurin series is. Well, can the symbolic processor in Mathcad Prime tell you that? You bet. Let's try something really simple like sin x. And I'm going to hit Control dot again. Well, it gave me that back. But what I can do now is I can type in the word series. There it is. There's a MacLaurin series. Now this is expanded about x equal 0. And it gave me the first couple of terms. I can tell it how many terms I want. I can go up to the 9th power if I want. Probably go farther than that if I really want to. Okay. There's no 12th power in this expression. Will it go to 13? Ooh, it did. Okay, it'll just keep going for me. And, whoops, there's the x to the 13th power. Now, very seldom are you going to need that many terms in a series. Let's stick with 5 right now. And let's go to 3. Now let's see what this looks like. I'm going to go ahead right there. I'm going to hit, this is the colon sign, all right? This says I want to assign something. I want to define something. And I'm going to define a function s of x. And so s of x is now the series approximation to sin x up to the 3rd power. Well, what would that look like here? I'm going to go up here to plots, insert plot, x plot, or xy plot. Right there, I'm going to put an x. I'm going to zoom out here in a second. And I'm going to say sine of x, and it goes from -10 to 10. Can I do that? Let's try it here. I want to see if I can do this without zooming out. I want to make sure that the letters are nice and big here so you can see them if you're looking at this on a phone. Okay, so there it is. That looks pretty good. Now, I can pick different integration limit or different plot limits if I want. Let's go from -3 times pi. So I can go over here to Math, Symbols, and I can hit pi, wherever that is. There it is. And over here, I'm going to go to +3 pi. I can also multiply it by, say, p, Control G. That also gives me pi. So there we go. I got a whole number of periods here for the sine function. So there it is. Well, what does my approximation look like? So there's sine right there. I'm going to go over to plots, and I'm going to add a trace. So I can add that. I'm going to put sx here. Well, 2 problems. Number 1, I have black over blue. Let's fix that. Let's go to trace color, and let's make that red. Okay, that I can at least tell which one's which now. Now, the other problem I've got is the vertical axis is just crazy big. So let's go from -2 to +2 on the vertical axis. There. That looks a lot better. So the red is my approximation, my MacLaurin series approximation to the sine, and the blue is the sine. Well, what happens if I add more terms? Let's go up to 5. Oh, look at that. Even better. 7. Even better. It's just, I love this. It's like a really bad video game. So you can see as I keep adding terms, the series approximation to sine just keeps getting closer and closer to sine. So there, I'm well past a full period now. There's no real reason to go beyond this. So I can do a series approximation of just about anything I want. Let's get rid of this. And rather than that, let's call this maybe, I want to do an exponential function. The x. There it is. Again, 11 is kind of a lot. Let's go to maybe 6. There's a 6-term series approximation. So let's see here. 1, 2, 3, 4, 5. So there's my 6 terms. Okay, so there's series approximations. Okay, let's try something different here. Now, I said before, I put it a series approximation to sine. And this is a MacLaurin series expansion. This is correct, most correct, at x equals 0. What if I don't want to expand it about x equals 0? What if I want to expand it about x equals 1? So I'm going to say x. And I'm going to say control equals. Let me go up here and show you where that is. If I go to Math, Operators, that bold right there, control equals, that's defining a variable for me. And I want to expand it about 1. Well, there it is. There's the same thing expanded about 1. What would that look like? I should have kept this, but I didn't. Let's go ahead and recreate this. Before, it was closest right around x equals 0 because I'd expanded about x equals 0. Once again, let me shrink this down a little bit. There we go. All right. Now the approximation will be closest to sign at x equal 1. Let's see what that looks like. Let's go back here again just to remind you. Say add a trace, s of x. So there I've got it. Now I had the same problem before. Let's fix these two things. I'm going to change the color, and I am going to change this from -2 to 2. I'll just leave the x limits. Wow, look at that error there. It's huge, but it's most correct there. Let's add a term here to increase the order of the expansion. Okay, closer, but it's closest right there at x equals 0. You can see it's not symmetric anymore. The error starts to get big right around x equals -2 on that side, but on this side it's good all the way up to x equals 4. That's because I'm expanding about 1 and not 0. What happens if I expand about 2? All right, interesting. See, now it's nice and close right in there. What if I expand about 4? Whoops, sorry about that. Now you can see it's really close around 4, and then the error gets big as I get farther away from 4. If I make this 0, now I'm back to a MacLaurin series expansion, and now that the errors are symmetric to the left and right of the vertical axis. All right, so let's go over this one more time. There's the math. There's symbolics. Look at all these different keywords and modifiers you can use. So I'm going to encourage you to go ahead and look through these. If you'd like me to do a follow-on that goes through more of those keywords and modifiers, I'm more than happy to do that. Just let me know in the comments. So there we are. I hope this helps, and we'll talk to you next time.